So the afternoon, in a certain sense, is going to be much lighter. I'm going to be talking about how to take into account robustness in interspace inverse dynamics. That's actually quite related to what we discussed in the morning. There's a force regularization task. As Ahmad was pointing out, in theory, having the inequality constraints should be enough to ensure that your robot is not going to slip, because the contact forces are going to stay inside the friction cone. But in practice, since all our models are wrong, well, the real contact forces may be exactly on the border, and so your robots may be slipping. And there are different ways to try to make sure that that doesn't happen. And one way that I'm particularly fond of is to work with robust optimization techniques to take into account the fact that your models are wrong, and so you can model these errors that you have in your model and introduce them inside the quadratic program that we have seen in the morning. So before going into the details of the math of how you model the uncertainty and you modify the optimization problem, let's just have a high-level overlook at what are the results that you can get. So I'm going to begin with a presentation that I gave several times about this paper I wrote with Nicola about 3-4 years ago now, which is called Robustness to Joint Torque Tracking Errors in Interspace Inverse Dynamics. So you can immediately see that we aimed at a very specific kind of uncertainty, which is the uncertainty that you have in the joint torque tracking. You can remember that the first thing that we discussed in the morning was the actuator model, right? We said actuators could be modeled as velocity sources, acceleration sources, or torque sources. And we said the torque assumption is the most reasonable one, because it's closer to reality, to the physics of the system, especially for electrodes. But the problem is that even if it's the best among the three, it's not a really good assumption either, because your actuator are not an ideal torque generator. So there's been a lot of work in how to make actuators that can generate exactly the torque that you would like them to generate. And despite all of this work, there doesn't exist such a thing as a perfect torque generator. So it's important, in my opinion at least, to take into account that we have discrepancies between the desired joint torques and the real joint torques. And in this work, I'm going to present one possible way to take into account these discrepancies. Okay, enough talking, let's start. So this is actually a motion that I generated using TSID, and I was given a reference trajectory for the center of mass of the robot, computed with trajectory optimization, then some reference trajectories for the feet. I basically used the same machinery that you have been playing with before lunch, and I could generate this nice simulation of the robot walking. Problem is, here we are in a controlled simulation environment where there are no noises, so all my measurements are perfect. I have no modeling errors, so the model of the robot that the controller has is exact, and I have no delays in the sensor measurements and in the control action. So you may wonder, okay, what is it going to happen if I start adding some noise in the joint torques of the robot? Well, the performance degrades pretty fast, as you can see there. Well, it'll take a while. And what if, instead of adding noise in the joint torques, we simply add a small delay in the estimation of the velocity? Well, that shouldn't be a big problem. Well, no, it is.
Or what's a small delay?
Small delay, I don't remember, 10 milliseconds.
Okay. That's big.
what if you introduce error in the initial parameters of the robot? So the model that the controller has doesn't exactly match the one that the simulator is using. Well, you see that things can go wrong pretty fast. So the key idea, as I already said, is to use robust optimization techniques to take into account that we have uncertainties. In particular, we have uncertainties in the joint torques of the robot, so in our control input. The question is, how do we model these uncertainties? Because we want to have a model, we cannot just say, okay, I have uncertainties. Well, there are two different approaches in the field of robust optimization. You can either model uncertainties as random variables. In this case, you need to know the probability distribution of these variables. Or you can say, I don't know the probability distribution, that's too much information. I just know that my uncertainties are bounded. So I can have a torque tracking error that is at most 10 Newton meters. Deal with it. Since we didn't know which approach was best, we tried both. And we compared the two resulting robust controller with the classic controller that is the one that you have used in the morning. So the idea is that you have the three robots, each one controlled by a different controller, and each robot is subject to the same uncertainty of the other two. So the comparison is always fair, because they are subject exactly to the same realization of the uncertainties. And even if the controllers only are aware only of uncertainties in the joint torques, we tested them also in the case of uncertainties like in the inertial parameters, delays in the velocity estimation, and limited torque bandwidth, which they were not aware of, but we just wanted to see if they were capable of performing better than the classic controller. Yeah, I should have cut the video because it's taking too much time. But eventually the guy on the left is gonna fall, I promise. Anyway, you see, okay, it's about to. Okay, even the guy on the right fell. But later, it is better. So, the conclusion that we found is that, well, the classic controller was the one performing the worst, and the winner was the robust stochastic controller, which, if you think about it, is quite reasonable, because the controller is aware not only of bounds, but he knows exactly the probability distribution of the uncertainty. So it knows that small errors are very likely to occur, whereas large errors are very unlikely to occur. So he has more information to work with, so it's reasonable that it performs better in the end. And you may wonder, okay, but robust optimization, that sounds fancy. I guess it's very computationally expensive, right? Well, not really. If you do things properly, in this case, we had a computation time of 0.2 milliseconds for the classic approach, which is surprisingly fast, and slightly higher for the robust work case, and 0.3 for the robust stochastic. So in particular, these results were not with the same code that you've been using, but it was a different formulation of the problem that we will see in a while.
It's solving one QP.
That's solving one QP, yeah. But it was a different formulation of the QP, and this computation time doesn't include all the computations. That's only for the QP, which is actually not a QP anymore in this case, but we're going to see that in a while. So, what's the idea of robust optimization? Let's suppose that we have a least square problem to solve, like the one we have seen in the morning. So we want to minimize the square of an affine function subject to linear inequality constraints. Okay. I suppose that we are working in a nice 2D example, and these black lines represent the inequality constraints. So this region here inside, it's a feasible set, and everything outside is unfeasible. And suppose that the solutions of ax equal a, which is basically what my cost function is trying to achieve, are represented by this red line here. So any point of this red line minimizes the cost function, but we have also the inequality constraint, so we want to stay between this point and this point, right? Any point on this line would be a valid solution of that problem. So if it was up to you, which point would you choose? Would you choose this point,
Middle.
this point, or this point? Well, middle, right? Because it's more robust. The problem is, depending on, if you just specify the problem in this way, well, basically you're letting the solver choose whichever point on that line, because they're all valid solutions. So it's not a good idea. And actually, since active set algorithms like the one used by AQuadProg, because of their internal functioning, they're much more likely to find a solution that is exactly on the border of the active set. And that's the worst choice for you, right? Ideally, yeah, you would like to stay in the middle. So we're going to see how we can change the TSAD problem so that we get solutions that are more like the robust one and not like the active set solution. So TSAD, just a quick reminder in case you had forgotten. That's how it works. You're given reference trajectories for whichever output function of the robot state you want to control, like center of mass, feet, hands, joint posture, and you are asked to find the joint torques, because that's in the end what you use on a real system. You want the joint torques to send to the motors that minimize the tracking errors for all the reference trajectories, while satisfying the rigid body dynamics, the rigid contact constraints, force friction cones, joint position velocity bounds, joint torque bounds. That's TSID in simple words, which we know that boils down in the end to solving a least square optimization problem. You've seen that in the morning. So the idea is we are going to model a torque tracking error that is additive on the desired joint torques. So instead of having x, we have x plus e, where e is the error. And we have already discussed that there are two options for modeling e. We can either assume it's a random variable, and we will use a Gaussian distribution with zero mean, because that's the only case that is tractable. Or you can assume that it is a bounded variable, in which case we will simply say that E is bounded by a certain quantity Emax, which is the maximum torque tracking error that we measured on our system. So let's look at how things are done in the first case, where E is a random variable. In this case, you get a stochastic least squares problem, where the main structure of the problem is actually the same, doesn't change much, but you have an additional term in the cost function which represents the probability that your inequality constraints be satisfied. Then for, let's say, technical reasons, which we will see later, we don't use directly the probability, but we take its log, which is very common if you're used to working with probability. That's because the log probability is convex while the probability is not. So it's better to work with convex functions than non-convex function in optimization. So basically, we have a problem that is very similar to the original one, but with an additional term in the cost function, which you can think of as a robustness measurement. And the parameter W, which is a weight, is a user-defined parameter that allows you to decide how much you care about robustness, measured by R, and how much you care about tracking the reference trajectories, which is defined by the classic least square cost function. So the good news, as I was saying, is that this function here is convex. So the problem is no longer a QP, but it's still a convex optimization problem, which is quite a nice object to work with, because we have well-developed algorithms for solving convex optimization problem, even very fast inside a control loop. The problem is that even if it's convex, computing this probability here, it's very expensive in terms of computation time, because you have no analytical solution for computing this probability. You have to use numerical techniques, which are very slow. So they can take something like 0.5 seconds for the dimensions we are interested in. And we don't have half a second to compute a probability every time we perform a control loop, right? So we cannot use this as it is. But what we can do is we can introduce an approximation, which is to say, I assume that the probability of all my inequality constraints being satisfied is roughly the product of the probability of any individual inequality constraint being satisfied. In other words, you can assume that all your inequality constraints are independent. Geometrically speaking, that's a very nice feature of the presentation. From time to time it jumps back to the first slide. Geometrically speaking, that's equivalent to assuming that your inequality constraints are orthogonal to each other. That's independence. So, okay, but how good is this approximation? Well, we're going to see later that it performs well in practice, but you can see it in action here in the 2D example that we saw before. Here, it's a feasibility set that we have seen before. And here, the color map represents the probability of satisfying the inequality constraint. So, of course, the probability is very high if you're in the center, because it would take a really large error to jump out, and large errors are unlikely to occur. And the probability gets smaller and smaller as you get close to the border. When you're exactly on the border, probability is going to be 0.5, because you have, if the uncertainty is on this side, you're going to be out. If it's on this side, you're going to stay in. So when you're on the border, probability is 0.5. And then when you move out, it gets below 0.5, and at a certain point, it's basically 0. So this is the real probability. This is what you get with the approximation. And if you just look at these two, I guess you cannot spot the difference. That's why I added the third graph, where you can see the difference between the two. And you can see that the main differences are at the intersections between inequalities, except for this and this, because in these two cases, the angle is exactly 90 degrees. So the assumption that the constraints are independent is true in that case. So yeah, errors are basically at the intersection, which is not a bad news, because those are points where you don't want to be anyway. So if the solver is doing its work right, it's keeping the solution inside this central area where the approximation works really well, because the error here is very close to being 0. So actually, this kind of approach may remind you of log barrier methods that are used for optimization, especially convex optimization. I don't know how many of you are familiar with log barrier methods. Okay, not many, so maybe you're not very interested in this comparison. But a log barrier method basically replaces your inequality constraint with a penalty function that tends to infinity as your solution gets closer to the border of your feasibility set. So this would be a log barrier, the green one. So it's more when you're far away from the boundary, and then when you get close to the boundary, it goes to infinity. And that's one way of dealing with inequality constraints. If you've ever used IP-opt, that's the method that's behind IP-opt. And instead, what we are doing here is that we don't have simply the log of the inequality constraints, as in log barrier methods, but we have the log of the probability of the inequality constraint being satisfied. So it's a different object, and the function that we get here looks more like this. So they share some similarity, but they're not exactly the same thing. Especially this guy here goes to infinity before you can violate the constraint, whereas this guy here allows you to violate the constraint. It just becomes high, and so it basically pushes you not to do that, but it can allow you to do it.
Is the stochastic optimization formulation where you do have the log CDF term, is that a direct, is that the same problem as the initial problem where you write it out with the two conditions, so that you've got that you're like b of x plus e is greater than or equal to minus v, I guess. So that kind of, so you had a slide where you had that, and then you produced your stochastic least squares problem where you introduced the r of x term.
Yeah.
Are they exactly the same problem, or is that a
there are some manipulation to do, and I'm going to explain that in more details later.
Okay.
So this is a sort of onion presentation where I go through the same material over and over, but each time with more details. I don't know if you like it.
That's good.
So here your W is, the trade-off is fixed, whereas log barrier, the trade-off actually tapers.
Yeah, and the W parameter would be changed through iterations, whereas here with W we just fix it.
You just fixed it.
Yes.
If you change W, that actually mimics a dual variable, then it's more of a Lagrangian form.
Yeah, we don't do that. We fix W and we keep it there.
Sorry. So why is it that you don't choose the log barrier method instead of the log CDF?
Because it's a different thing. It's a very different thing. I mean, this comes from all the modeling assumptions that we have been discussing so far. This is simply a numerical technique to solve inequality constraints optimization problems. So it doesn't have the same meaning. Here I have no probabilistic interpretation of the solution, and I have no exact control over what's going on. And as JJ was pointing out, actually in log barrier methods, the W parameter, typically you make it convert towards 0 as you keep iterating, because in the end you want this function not to affect the solution. So interior point method allows the solution to converge towards the boundaries of the feasibility set, whereas we don't want to do that. So it's a very different spirit behind. I was just pointing out that there might be, they might look similar, and since this is very well known in optimization, I pointed it out.
But do you lose the property of satisfying the inequality constraint because of this?
That is why, it's not that you lose it, that it's simply that I lose control over my presentation. That's for sure. That is why here we kept the original inequality constraints are still there.
Ah, it's still there, yeah.
So thanks to this, we can be sure that we will not violate them. And this on top is going to ensure that I will not be exactly on the border, but how much far I will be from the border depends on W and also on capital A and small a. So the other approach that we mentioned before was to say, I don't know the probability distribution of my error, I just know that they are bounded. So what you do in robust optimization, which I also call worst case optimization, is that you want to satisfy the inequality constraints for any value of E that is less than or equal to Emax. So you want to satisfy your constraint for the worst case scenario. It's a very pessimistic approach if you want. And we're going to see that this problem here, which is not a problem you can just solve in this form because you have an infinite number of constraints, can be reformulated into just a least square problem, a standard least square problem. And we're going to see how you can do this derivation later. But before going into the math, let's see a bit how that looks. So in order to evaluate the performance of the robust controllers, we ran thousands of simulations. You already know the final result because I gave it up before. This is just a small subset of the simulations that we ran, just to give you a taste of what it was. And as you can see, the robots controlled by the classic approach are falling much more often than the ones controlled by the robust controllers. So even if this is just a subset, I chose the example in such a way that they are quite representative of the final statistics.
So why is the worst case robust one worse? I mean, why occasionally there happens to be a failure, whereas you would expect?
Yeah, that's a very good question. That's a very good question. And I always get this question because I always forget to explain it before showing the video. So the reason why even the two robust controllers can end up having the robot falling, well, first of all, in the simulation, we introduced errors of which the controllers are not aware. So there might be modeling errors, delays, or noises that the controller is not aware of. So in that case, it shouldn't be surprising that the robot can fall. But the tricky part is that even if you introduce only the uncertainties that the controller is aware of, still the robot can fall. And the reason behind this is basically what I was telling you in the morning, that TSIG is quite stupid. It's a very myopic control framework. It's not an optimal controller that looks far into the future and is able to predict the results of its current action. It only looks right now, what are the acceleration that you would like me to track, what are the constraints, what are the probabilities that I will violate the constraint, and let me try to find a trade-off between all these conflicting objectives according to the weights that you gave me. And this is not smart enough to make sure that you never fall in practice. Especially one example that could make this more clear is that if you increase a lot the weight associated to the robustness measurement, the robot is going to basically choose always the most robust thing to do. But the most robust thing to do might be just to do nothing. So you might have a reference trajectory moving forward, and the robot might say, no, I'm going to stay here, because that's the most robust thing to do. And of course, that's not a behavior that you would like your robot to have, right? So it's quite myopic, again. And even if we introduce these robustness measurements, they can improve the behavior on average, statistically, but there is no guarantee that things are going to work out.
Yeah, I understand that it's false, but why is the worst case? The worst case seems to be
Worse than the stochastic?
yes, and it seems to be like more on the robust side than the.
You see, okay, you see, you're saying the robust worst case should be more conservative, so it should fall less often. Okay, the reason why that doesn't happen is that many times in practice, there is no solution satisfying the inequality constraints for all possible value of the uncertainty. So in that case, we will see that later, we relax the robust constraint and we basically reformulate it saying be as robust as you can. But being as robust as you can is basically what the robust stochastic is doing, but the robust stochastic knows the probability distribution. So it knows that it's much better to be robust to small errors on all variables than to be robust to a large error on one variable and to zero error on another. So it can take decisions with more based on a richer information. That's why it happens.
So how do you set the Emax? Does it correspond to like 50% probability? Or?
In practice, I set it to 3 times the standard deviation.
3 times, okay.
So it's 99.
Yeah.
It's very high probability. But as I was saying, most of the times it cannot find a solution that satisfies the inequalities for all possible values of E. So it tries just to be just saturate.
Because this bound affects the so-called stability or something. This bound directly affects it.
Yeah, but I will show you later how it's formulated so you can have a better understanding. So these are just tables summarizing all the tests that we did. Each line corresponds to 300 simulations, and each line corresponds also to different uncertainties that were introduced. I don't want you to go and read all the values, but just to know, we introduced uncertainties in the velocity estimation, in the torque tracking error, the torque boundaries, and the inertial parameters. And we tried different combinations of these uncertainties, but in the end, the results were always the same. If you look at the number of faults, the last 3 columns, you can see that the classic controller falls much more than the robust stochastic and the robust worst case approaches. Then we also repeated the same analysis using not a locomotion task, but a manipulation task. So we picked drilling. Again, we performed thousands of simulations, and in the end we found results that were very similar with the ones we got for locomotion. Okay. So that was the light part of the afternoon. Now let's go into the math, shall we? So this second part is not going to be much about robotics. It's going to be basically a very small and humble tutorial about robust optimization. I say humble because that's not at all my specialty, but I had to learn a few things to do this work, so I think there are interesting tools to know of, regardless of whether you want to apply them to TSID or other kinds of optimization problems. They're interesting tools. So that we already know. I'm gonna first go into the detail of the worst case approach, and then we're going to see the worst case stochastic. So the idea, as we already seen, is that we assume there are additive uncertainties on the joint torque. So the real joint torques tau is actually equal to the desired joint torque, which is the one selected by the QP solver, plus an error E. And we assume that this tracking error belongs to a set. Let's call it U, the uncertainty set, U. And since it's a very reasonable assumption to say that the tracking error at one joint is independent of the tracking error at another joint, well, this means that basically my uncertainty set can be a hyperrectangle, because all constraints are independent, all joints are independent. So we model U as the set of values that are less than a certain quantity in absolute value. That was clear at the beginning. So Emax is the maximum torque tracking error. How do we get Emax? Well, you just run a few experiments on your system. You measure the torque tracking error. You look at the maximum you got. That's a good initial guess for Emax. So the robust least square optimization problem looks like that. We have the classic least squares cost function, but the inequality constraint this time has this extra term here, E, which is not a variable of the problem. It's just the uncertainty, and we would like this to be satisfied for all possible values of E. So that simple writing there actually hides an infinite number of constraints, because you should think that you have one of these constraints for each possible value of E inside U. And since E is a continuous variable, well, there are infinitely many possible values of E. So you cannot just solve that problem.
I thought that E was taken to only be this kind of box of the maximum error, though. So
U is a box.
U not a finite set?
U is a box. E is just whatever possible value inside that box.
So actually E is like uniformly sampled from the box. This is the worst case.
You're thinking in terms of probability distribution.
Yeah,
Here you should be thinking in terms of set membership.
I see.
You know nothing about the
So
probability
it's just an infinite
distribution.
number of constraints, and that's how you
You
formulate.
just know the uncertainty is inside this set. You don't know the probability. It may be uniform.
Mhm.
That's also how I think about it. But it may be different. It doesn't matter.
Okay.
So yeah, sometimes you may wonder why I didn't add also the error inside the cost function, and then I could try to minimize the maximum of the cost function over all possible values of E. That would be a classic worst case approach, but that could result in a very conservative behavior in terms of tracking of the reference trajectory, so I simply decided not to do it. I didn't even try, so don't ask me how it looks like. Yeah, we should be aware that the problem, as it is formulated here, could be unfeasible, because there may not exist any value of x that satisfies this equation for all possible uncertainties. Like if my constraint is x between 0 and 1, and my uncertainty set is between -1 and 1, of course there is no value of x that satisfies the robust constraints. And that's really important for us because we are doing online control, at least that's the application I have in mind. So you don't want to try to solve an infeasible problem inside a control loop, because once the solver tells you, sorry, the problem is infeasible, what are you going to do? It becomes a bit problematic. So first of all, let's see how we can transform these infinitely many constraints into something that is tractable, so a finite number of constraints, because that's what we know how to solve, or at least numerical solvers know how to solve. So these are the original constraints, which are infinitely many. We can simply rewrite them as a finite number of constraints by using this reformulation, which is actually very simple. It just says to have this satisfied for all possible values of E. Well, it's the same as saying that the minimum value of this guy, which actually is the worst case, for all possible values of E, is greater than 0. Is this clear for everybody? Okay. And I just rewrote it for each single constraint. So BI represents the ith row or element of the matrix vector, capital B, small b. So I want to have this satisfied for all my constraints from 1 to m. Okay, now I have a finite number of constraints, but still they don't look very tractable, right? Because it's an optimization problem that I should put as a constraint of another optimization problem, so it's a nested optimization problem. I don't know how to pass that to a solver. The good news is that actually this is equivalent to this. And if we think a bit about it, I think we can understand how I got from there to there. So here we are taking the minimum with respect to E, which means that everything that doesn't depend on E, we can take it out of the minimum, right? So the term BI times X and the term BI, they can get out. BI times X plus BI, we can take them out. So we are left with the minimum of BI times E for E in absolute value less than E max. So what is the minimum of a linear function, of a variable, for the variable being inside a box? Well, it's always going to be in a corner because it's a linear program. And if you know something about linear programming, you know that the optimum is always at the vertex of the feasibility polytope. Which makes sense. You want to minimize a linear function over a polytope. Well, if you keep going in one direction, you will end up in a corner of this polygonal shape. How do we select which corner it is? Well, this is basically just the sum of the products between the elements of BI and the elements of E. So if the element of BI is positive, well, the worst case in terms of minimizing is that E is negative. Because positive times negative is negative. So we want to minimize, we want to go down. If instead the element of BI is negative, then the minimum, I get it when E is maximum. Okay? So in the end, what I want to have is minus the absolute value of the elements of BI times E max. That's the solution. I don't know, maybe it was too difficult to explain just using words, but I think if you think about it a little bit, maybe you go read the paper where it's explained more carefully, you can figure it out. Also having a geometric interpretation can help a lot.
So potentially if you treat E as another, like say, decision variable, these are just another set of inequalities, right?
If you take E as another decision variable,
It's like a slack or something.
you mean you add E as a variable of the
But it's
outside
not in the objective,
optimization?
Not in the objective, but only in the constraint, then if you toss into a solver with inequality constraint.
But the problem is that it's not only that you need to add E, you need also to solve an optimization
Right, right.
problem
No, I'm
inside
just
the
saying,
constraints.
as an alternative to your minimization. So I don't involve another minimization. So
Okay.
I don't go through this, but just treat E as a decision variable. Just add another set of inequality to the original problem. That
If you do that, if you let the solver choose the uncertainty, the error, it's going to choose the errors that fit its needs. Instead here, it's exactly the opposite. We want to choose the worst case uncertainty, and we want the optimization to reason taking that into account. So it would be a best case approach, not a worst case approach, what is suggested.
This would not work if you generalize this to this box type uncertainty set to like say a polytope. Right?
If
If
you
you
have
multiply
if
E
you
by
have a
something.
polytope, actually, I don't remember exactly how it goes, but in the end you still get a QP. In the end you still get a QP. It doesn't change the shape of your problem.
It wouldn't change. It's still that.
It's not as simple to derive as I just did. This is quite intuitive, and maybe some of you managed to follow through my explanation. When you have the uncertainty set, which is not a simple hyperrectangle, then it's a bit more convoluted, but not too much. I think it's explained in Boyd's convex optimization book.
Okay.
This was an example.
Yeah, I was just thinking initially that could be just directly treated by a QP solver. Just write that absolute value as two inequalities.
Yeah, you can solve this with a QP solver.
Initially, the initial problem.
If you put E as a variable of the initial problem,
Yeah, exactly.
then it's not going to work because the solver is going to choose the best case for the uncertainty. Instead, we want the worst case.
Okay.
So you can choose different bounds for each dimension of E, right? Here,
Yeah.
Here it's isotropic, but you can.
So Emacs here, it's a vector, it's not a scalar. So Emacs is a vector, you have a different maximum value for each element of E. Yeah, sorry,
Right.
I didn't make it clear. Yeah, you don't have to have the same torque uncertainty on each
Right.
joint. You can set small values for the small joints and big values for the big joints, for instance.
And does it make sense to have different positive and negative bounds? No.
You could, it doesn't change much. You just need here to take care of that because in the case where
Yeah. You
B
would
is
have.
positive or negative, you have to choose one or the other, but it's kind of the same stuff. Okay, so we went from an infinite number of constraints to a finite number of constraints, and we got lucky because they're still linear. So the shape of our problem hasn't changed. We get always linear constraints. The cost function was the same from the beginning. And so we can rewrite this robust least square as a standard least square taking this form. But now we still have one problem to solve, which I mentioned before, which is that this problem here could be infeasible because there may be no value of x that satisfies this inequality. So we want to modify a bit the problem so that when the constraints are infeasible, we still get a solution. So ideally we don't want just to get a solution, we want to get a solution that is as robust as possible, right? So the way we modify the problem is actually very simple. We just introduce a scalar slack variable s, which allows the solver to choose how much robust it can be. And the scalar variable x multiplies this term here, which is the term that basically introduces the robustness. And we want to, since we want to maximize s, but we have a minimization problem, we minimize minus S times a weight. And typically one would choose W to be quite high, so that first of all the solver tries to be robust as it can, and then in the null space of this it tries to track the reference trajectories, which is represented by this term here.
So S scales the robustness, the amount of robustness.
The robustness margin. You can think of that as a scaling of the robustness margin. How far away you want to keep from the boundaries of your feasible set. So yeah, typically we set S to 10 to the power of 6. So the interpretation is, if possible, set S to 1, and you get the same as the robust constraints we saw before. Otherwise, set S, decrease S as little as possible. And if it's really necessary, the solver is going to set S equal to 0, and in that case we get exactly the original non-robust constraint. So yeah, you get basically an interpolation between the robust constraint and the standard constraint by making S vary from 1 towards 0. And in this case, you have the guarantee that if the original problem was feasible, then this problem is also feasible, because by setting S equal to 0, they are the same. So we solved also the second problem of feasibility. Okay, to summarize, we started from the assumption of additive uncertainties on the joint torques. We assumed that the tracking error belonged to an uncertainty set U, which we decided to model as a hyperrectangle, because each joint has an error that is independent of the other joints. We formulated the robust problem, and we saw that it was untractable because you have infinitely many constraints. But we saw that it was easy to reformulate that as a standard least square problem. And finally, we handled the case of infeasibility by introducing a simple slack variable. So the final problem is always a least square program with just one variable more than the original problem. So in terms of computation time, it doesn't change much. Yeah?
So just a question, so in the TSID formulation, so tau is only a subset of the decision variables. So is this what you propose specific to tau, or can it be extended to the other?
So that's a question I was hoping not to get until the end. For some reason that I find hard to explain just using words, to work with this kind of robust approaches, you cannot use the formulation that I presented this morning, the one where you remove tau from the optimization variables. You cannot even work with the original one where you have all the optimization variables. You need to do the opposite of what I presented this morning. That is, you need to remove the accelerations and the forces from the optimization variables. So you need to reformulate the problem only as a function of the control torques tau. So when I write x in my slides here, x actually are the joint torques tau, because I reformulated the problem as a function of tau. That's not a good idea in general, because doing this formulation is quite expensive. You need to invert the mass matrix, for instance. But it is necessary for formulating these robust TSID problems. And maybe later I can try to explain you why in more details, but now I prefer to get to the end of it and see what time it is.
But it's okay to add the uncertainty in the states?
By state you mean?
Like joint positions, for example.
So the joint position and velocity are not variables of my problem. They are measurements. So you cannot do that. You can, if you want the uncertainty to be as simple as it is in this case, so simple additive linear uncertainty, you can only add it on the variables of your problem. So the accelerations, the contact forces, and the joint torques. And the reason why I picked the joint torques is that I thought it was easier to characterize the uncertainty on the joint torques than to characterize the uncertainties on the joint accelerations or the contact forces. Because the uncertainty you have in your joint torques may depend on your actuator. And since you typically spend 1 year designing the torque control of your actuator, you should know very well how well it can track and what is the maximum tracking error you have in the joint torques or the probability distribution, this kind of stuff. It's mainly a convenience choice.
But in the simulations, you're actually introducing perturbations on all of the parameters, aren't you?
Yeah, because I mean.
Yeah. Is that also, have you found that the uncertainties in the joint torques is the most kind of problematic? Or do you just make the other uncertainties smaller?
Not necessarily. In simulation it's not, because in simulation I insert it simply as an additive Gaussian noise. In real system I think it can be more problematic because it's not a white noise, not at all. It actually depends on the state. When you're at zero velocity it's much higher than when you're in motion because you have static friction. It can be higher than Coulomb and viscous friction. There are reasons that led me to this choice. I've been working a lot on torque control and low-level actuator control, so that's why I went in this direction.
For the stochastic formulation, it seemed the only addition was this cost, right? So why could you not put that into the TSID formulation? It's only the cost function then.
I could. The problem, I mean, we're going to talk about the stochastic right now, and the reason why it's not implemented in TSID is that the problem is no longer a QP with the stochastic approach, whereas it is a QP with the worst case approach.
But the problem with the elimination of the torques in the formulation doesn't show up when you only have it as a cost.
I didn't get the question, sorry.
So with the box constraints, it's a problem because you change the constraints that you have to formulate everything in terms of torque. But with the stochastic formulation, you only have a cost and the constraints stay the same.
Yeah, but that is not the reason why you need to reformulate everything in terms of the torques. It's a different reason. If we get alive to the end of this, I will try to explain it. Any more questions about the worst case approach? So we have 25 minutes left. Okay, then we should be right on time. So let's talk a bit about the stochastic approach. Same initial assumption, we have an additive uncertainty in the joint torques, which I have revealed they are the variables of my problem in this formulation. Again, we assume that the errors are independent of each other. There is no reason to assume coupling, unless you have coupling in the kinematics of your robot. In that case, you might want to do that. But in this case, we assume that the error is a random variable, and we know the probability distribution. So it's zero mean, and it's Gaussian. And we will also assume that the covariance matrix is diagonal, because the errors are independent, but actually that is not required. You can do exactly the same. All the math that I will show works the same, even if the covariance matrix is not diagonal. So let's take a look at the problem now, knowing that E is a random variable. So this is a problem. This time I also added e in the cost function, not only in the constraint. And since e is a random variable, well, also the constraint and the cost, they are function of a random variable, so they are random variables themselves. So what does it mean to say I want this random variable to be greater than 0? It doesn't mean anything. You cannot say a random variable is greater than 0. It's a Gaussian random variable. It has an infinite support, so it can take any value from minus infinite to plus infinite. There is no way to make sure that it is greater than 0. So the problem formulated in this way doesn't make any sense anymore. So we need to write it down in a different way. And a very classic approach for dealing with the cost function is to say, well, instead of minimizing the cost function, we minimize its expected value, right? If you have seen LQG, linear quadratic Gaussian regulator, which is a stochastic version of LQR, that's how you do it there, right? Well, the problem is that if you take the expected value of this, you basically go back to the original cost function plus a constant term, which then doesn't affect the optimization. Say minimizing f of x or f of x plus 2, you get the same x in the end. So it seems that introducing the uncertainty in the cost function is not really interesting. So what is interesting instead is to look at the inequalities. And here the classic approach is the one that is used in chance constraint programming. That is, we replace the inequalities with the probability that the inequalities be satisfied. This is something that makes sense and we can work with. So we have this probability, and this probability of course depends on our choice of x. Because if you choose x that is further away from the borders of our support polygon, well, we have a higher probability of satisfying the inequality constraints. So what do we do with this p of x? Well, first of all, in general, it's not convex, but I already told you the trick to make it convex. The trick is you take the log of p of x and it becomes convex. That's true for the Gaussian distribution, and it's also true for a lot of other distributions. But then we have the log probability, which we call R. What do we do with that? And what we choose to do was to add it to the cost function. In chance constraint programming, typically that's not how they do it. They typically add it as a constraint. So they say they put R of x greater than a certain value. So like I want the probability of my constraints being satisfied be greater than 90% or 95%. But I found that for our application it was more flexible to simply add it in the cost function and have this knob that the user could play with to find the right trade-off between being robust and tracking the desired trajectories. Okay, so we have this problem. It's convex because R of x is convex. And we decided to keep the original deterministic inequalities because we saw that this alone is not enough to ensure that you satisfy the inequality constraint, because it doesn't go to infinity as you approach the boundaries of your feasibility set. It simply penalizes you. But if you remove the standard inequalities, you may have a solution that violates them, which is not a good idea in general. Yeah, another alternative which we didn't explore, would be to use a prioritization approach. So you could try like to first minimize this and then minimize this subject to the constraint of keeping this fixed, or the other way around. Could go nuts with different options, but we thought that this was the best way, because as you make W tend to very large values or to very small values, you're basically approximating the two different prioritization schemes that you could select. And it's also much simpler and computationally faster to use weighting rather than strict priorities, as we discussed already in the morning. So the main problem, as I mentioned before, is that even though this is a convex differentiable problem, which is all nice, still you need to compute this probability there, and there is no analytical way of computing it. So the only thing you can do is that you can use numerical techniques, but they are very slow. So you cannot do that inside a control loop. And the idea is that we can approximate it with the product of the probability of the single inequality constraints. So it comes back to assuming that the inequality constraints are independent of each other, which is not true, but it's not too far from being false. Not too far from being true. Hopefully it's far from being false. This is another interpretation, if you prefer. It's equivalent to neglecting the off-diagonal terms in the covariance matrix of, not of E, because E has no off-diagonal terms, but of this guy here, B times E, which is still a Gaussian random variable, but this time the covariance matrix has also off-diagonal terms. So thanks to this trick, we can just evaluate m one-dimensional probabilities instead of one multi-dimensional probability. And it turns out that the one-dimensional probability is very simple to evaluate, whereas the multi-dimensional one is very time-consuming. So this is much faster than the original problem. Still, we need to evaluate the one-dimensional probability. So how do we do that? Well, we write down the probability we want to compute, and then we write it down in terms of this variable here, EBI, which is nothing more than the product of BI and E. And a linear combination of Gaussian random variable is still a Gaussian random variable, luckily for us, which has still zero mean as the original variable, but has a different covariance matrix, which is you can compute using that simple expression over there. And there you can see why it has off-diagonal terms, because it's the product of BI times BI transpose. And then you can, since it's symmetric and zero mean, this guy here, it's equivalent to this guy here. So of mean greater than a certain value is the same of being less than the opposite of that value, because it's symmetric around the origin, zero mean. And then you can rewrite this in terms of this function here, which is the cumulative density function, CDF for short, which is basically the integral of the PDF. And here the bad news is that most univariate distributions have an analytical expression for the CDF, but the Gaussian, which is the most used and well-known one, well, it does not. That's something that I discovered when I started working on that. I didn't see that coming. Because basically you will need to compute the integral of E to the x square and there is no analytical solution for that integral. It looks a very innocent, simple integral, but it's nasty. But luckily for us, there are very accurate and fast approximations. Actually, I found many papers that were proposing ways to approximate that integral that are fast, and basically they boil down to evaluating a polynomial. So it takes a few micro or nanoseconds. So, end result, you get this function here to evaluate, a bunch of those, and for evaluating those they correspond to polynomials. You don't need to implement them. I was using the ones that are provided in SciPy, for instance, when I implemented this, and you can probably find them in any numerical computing library. So that is the final robust optimization problem with the stochastic approach. And I think that is the very sad end of my slides. But good news is we are 10 minutes early. So I can take questions, or I could even try to explain you why you need to formulate this as a function of the joint torques when you have the robustness. Yeah.
So you say that for TSID it only only consider one time step, right? So I'm curious about how you use that to plan the walking step, or to control the robot to do the walking. You say that you give the reference trajectory, and so how do you plan that trajectory using different approach from TSID?
So for that specific case, the reference trajectory, I computed it in a very smart way. I went to the office next to mine, and I asked a colleague of mine to give it to me.
Okay.
That was super fast. It's very computationally effective. I suggest you do that if you can. Otherwise, you can use trajectory optimization. In that case, it would be simple because it was computed using the linear inverted pendulum model for approximating the robot. So you approximate the robot as a linear inverted pendulum. You have a linear dynamics for the center of mass. So in the end, you are solving again a QP for computing the trajectory of the center of mass. Then you need to compute the trajectories of the feet. That has been done heuristically by using polynomials that simply interpolate from one footstep to the next one. And that's it, nothing more.
So from all the other methods, basically you have a reference trajectory and you try to follow that by time step by time step.
Yeah.
And another question is, besides TSID, which you formulate the problem as optimization problem, how do the other people solve this control problem or similar control?
So TSID is very, very, very common.
Okay.
So I think that most people that are making a robot walk are using TSID in one of its many variants. Another approach would be to just do inverse kinematics, which means that at the first slide of my presentation this morning, you say, I want to use velocity control, or I want to use acceleration control. So you are starting from a different assumption for modeling your actuators. But in my experience, the other models are less accurate, less reliable, so you would end up having problems probably at a certain point later down the chain. But it could be feasible for certain cases. Like for quadrupeds, I know that often people don't model the whole dynamic of the system, because you can very well approximate the quadruped as a single rigid body, where the legs are without any mass. So you neglect the mass of the leg, you assume all the mass is in the main body, and so you have a simplified form of the dynamics, which allows you to simplify basically the TSID problem. instead of optimizing for accelerations and forces, you optimize only for the forces. But I see that as only as a simplified version of TSID. So I'm not aware of any other approach that I could recommend people to use apart from TSID in one of its variants. Maybe, I don't know if somebody in the room disagrees with that among the more senior people.
You can take maybe just a little bit of care to say that it is at the cutting edge of the state of the art. So the manually tuned methods that are relying on simple model are maybe yet working better in practice. If you untune the controller of HRP2 or the gate controller of animal, that's the way you get the best solution right now. And we are not exactly sure what is in the robot of Boston Dynamics, but it's very likely that there is a lot of hand tuning there, a lot of controllers that are not too complex, not too relying on numerical optimization,
Yeah.
but on a lot of parameters. And they are very strong in benchmarking, in making good idea of the motors that then they can tune properly. So the idea that we would like to be able to do the same, but with 10% instead of 100%. For that, having something automatic is the way to go. But it's, well, we are still not able to demonstrate the same efficiency as we can.
Yeah, there is one exception that I just remember about. It's admittance control. So actually, most of Japanese robots, which work really well, they don't rely on TSID. They rely on admittance control, which is one way. It starts from let's say velocity control, so the assumption that I said this morning is not really good. But then it works really well because on top of that they add a force feedback loop. So they try to track at the same time the reference joint trajectories and the reference contact forces. And if you do that with the right tuning, with the right gains, it works really well in practice. So actually, I think those are the best working robots we have seen, excluding Boston Dynamics, which we don't know how they work. And those are not based on TSID. So TSID is stronger theoretically because it derives the equation of motion. You can have proof of the stability convergence and whatever. But in practice, other more heuristic-based methods seems to be outperforming TSID. Of course, it also depends a lot on which platform you're working. TSID can to work well needs to have a good torque tracking. If you don't have a good torque tracking, then maybe TSID is not a great idea. It's better to use admittance control.
Was that for this robust modification? Did you try it on the hardware and did you see big results?
No, I haven't tried it on the hardware. At the time where I was doing that, HRP2 was not torque controlled, so I couldn't apply this approach on the hardware. And as far as I know, nobody has ever tried it on hardware. So it remains a theoretical tool to be proven to work well experimentally. Yeah.
In the simulations that you showed, the uncertainty was only at the joint torques?
No, in the simulation we were simulating also other kinds of uncertainties.
Like inertia parameters?
Yeah. Yeah.
Could you imagine using the same technique for, let's say, second order inverse kinematics, where you assume uncertainty on the acceleration, and then in that case you could imagine deploying this on a hardware, a more classical hardware?
Yeah, actually, you can use TSID and then have a positional velocity control on the real hardware, because instead of taking the torque commands and sending it to the motors, you could take the accelerations, integrate them as we did for the simulation this morning, and then take the integrated values as a reference for the motor controller.
Okay.
So that's actually how many of the experiments at last have been done.
Okay. But could you make it simpler and start, so from the start just run inverse kinematics and assume you have a perturbation on the joint accelerations and on the torque?
Yeah, you can do it, it's all the same. The only problem I see with that is if you're working at the kinematic level, you don't have the forces in your problem, so you cannot ensure contact forces to be inside the friction cones. So that may be a problem. Okay, well, it's just 3, and I would be for not ruin this nice light lesson trying to explain you complex stuff I'm not sure I can explain. Let's say it's done, and we go to the social event.